Letitia has we're going to talk about yesterday's homework before we start today's lesson because I just want to make sure everybody tried it. It's not that hard, but and I did find a little shortcut on the calculator. Some of you might have already known it. But so we were talking about the cardboard that Letitia has. It's a 12 by 18 inch sheet of cardboard. She wants to create a box with no top by cutting congruent squares out of the corners and folding up the sides. What function does Letitia have to maximize to create the box with the largest volume? What is the domain of the function? Then we're going to find that volume and we're going to find the height or the size of squares. Okay, so she has a rectangular piece of cardboard that's 12 by 18 inches. So we got a rectangle. There's the shape. And then she's cutting out we know it's 18 inches on one side and 12 inches on the other. And she's cutting out the corners, but we don't know the size of those corners. So referring back to what we did yesterday, in the example, we know that that size is then x, this length. Now, she's going to fold up those sides. It's kind of like putting together a little puzzle or, one of those little toys you get where you have to put it together. You fold up the sides, and now once these corners meet on the sides, you have a box. You tape it together or something. But the problem is, we don't know how much she has to cut out to make the biggest box out of this piece of cardboard. What size squares does she have to cut? First it says, what function does she have to maximize? Well, the function we're talking about is volume. So number one, the function we're talking about is volume. So number one, volume, which is length times width, the base, times the height of the box, which is our x. Height is x. So in this problem, our x is going to stand for the height of the box. When we put it in the calculator, we have to remember that x is our height. And then since our function is volume, the y is volume. What is the domain of that function? Well, the most she could cut out is the half of the shortest side. The shortest side is 12. If she cuts out more than half of that, she wouldn't be able to make a box. So the largest x value has to be less than 6. So the domain is between 0, because if she cuts out 0, she wouldn't have a box either. So x has to be greater than 0, but less than 6. We're not going to worry about the range. That's part of the shortcut for the calculator. So what size squares? So number 2, we have to figure out what size squares she has to cut. Well, let's write out the function. We know that the volume is length times width times height, and we know the height is x, but we don't know the length. Well, if you're cutting out a square of size x from both ends of each side, you're subtracting x on this side and x on this side, so you're essentially subtracting 2x. So it'll be 18 minus 2x for the length and 12 minus 2x for the height. So we're going to have our volume, or f of x, volume, is x, our height. I put that in front just because it's an x by itself, times 18 minus 2x times 12 minus 2x. Remember, this is the length of the box, and this is the width of the box. We'll need that. No, we won't need that for this problem. Okay. So what size squares and what is the volume we're going to find by putting this into the calculator. So on your calculator, you're going to enter that function in the y equals menu. Make sure all your stat plots are off. So you've got x times 18 minus 2x times 12 minus 2x. And then instead of going to your window and resetting that, we're going to use which I had forgotten about, thank you to my student who reminded me, zoom, and then if you go down 1 on here to the bottom to zoom 0, oh, did I go too far? No, zoom fit, that will fit the window to your function. So you don't have to actually do it yourself. So the window is automatically going to be adjusted. If for some reason you still can't see the maximum value of your graph, you can always zoom out once. So you hit zoom 3 and zoom out, Have to hit enter again. And now you can definitely see it, and you can see more of the function. So we're gonna, it doesn't matter which screen you use, this is fine too. So now I'm going to hit the second trace to get to the calc screen, and I want the maximum, so I want number 4. And I just want to set my left and right bound, so see your spider's right there. You want to move it a little to the left of the maximum value, and then move it over the top of there to the right a little bit. And now we know that our maximum is somewhere between these two boundaries, so we can tell the calculator to guess. So the maximum x value is 2.35, and the maximum y value is 228.16. So the x equals 2.35, and the y is 228.16. Well, if you go back to what our variables stand for in this problem, we said x is the height, or the amount we cut out of the squares of the sides, and y is the volume. So the answer to our question, the number 2, answer to number 2 would be 2.35 inch, was this inches? 2.35 inches. And the answer number 3 would be 228.16 cubic inches. So the answer number 1 was actually this, the function 2. This is the answer number 1. This is the answer number 2. This is the answer number 3. Now I want you to turn to page 169 in your book and try this problem from start to finish. So set up your problem, draw the picture, enter it in the calculator. Stop the video and try that problem. Okay, so you tried the problem, you drew your picture. It's a rectangular sheet that's 40 by 50 centimeters. So this is 50, this is 40, and I'm cutting out the corners. And I'm taking x out of each corner. And then I have to fold up the sides to make a box. And when I rewrite when I write the length and width of the box, I remember to take 2x away from each of the original lengths. So 50 minus 2x is the length, and the width is 40 minus 2x. So our function is going to be our height, which is x, times my length, which is 50 minus 2x, times my width, which is 40 minus 2x. So that's your function. And the domain is going to be half of the shortest side at the top and 0 at the bottom. So the domain is x has to be greater than 0 and less than 20. Half of 40 is 20. Okay, so that's answer number 1. Number 2, we just put this in the calculator. So back to your y equals menu. You can clear, or you can just type over the numbers you had in there before. Just make sure they're right. So 50 minus 2x and 40 minus 2x. And then hit zoom 0. And you can see that maximum, but I'd like to have it a little better, so I'm going to zoom out. And now I can see that the local maximum is right here. And so I'm going to hit second trace, number 5. And my spider is already to the left, but I'm going to move it just a little more. I think I'm doing the wrong thing. Second trace, number 4. Sorry, I was looking for an intersection. Our left bound is going to be here, and then move it to the right of that maximum. Okay, and then press enter. I'm going to move it a little more. And press guess. Tell it to guess. So you have a maximum at 7.36 And for your height and your volume, maximum volume is 6,564.23 centimeters cubed. So number 2, the height, or x, is 7.36 centimeters. And the maximum volume is 6,564.23 centimeters cubed. Remember, our volume was our y value. Y equals volume, x equals height, the amount that you cut out of the corners. So that's how you do that problem. We'll do one more of these tomorrow so that you're ready to do this on the test next week. Okay, starting today's work, you're going to go to page 171 in your book and try this warm-up. Okay, so we're going to put 2 equations in our calculator. So it says graph each equation on the same coordinate plane. And then find how many points of intersection there are. So if I graph them both, you'll enter them both in the y equals menu. To get the fraction, you just hit alpha y equals and then choose number 1. So I put it in my y equals menu already. And then you press graph. I'm going to press just zoom 6 for now to see if they both fit on the main screen without any window adjustments, and this one does fit, so we'll just leave it like that. And I can see the second graph looks like this. That was a linear equation. The first graph was a quadratic, and it looks like that. There's 2 points of intersection because they cross in 2 spots. So graph each equation, we did that. How many points? There are 2 of them. How long will it take the paintball to cross the path the ball traveled? How long will it take the paintball to cross the path the ball traveled? Well, if we look at our graph, the paintball hasn't really taken off yet, and so it's going to cross right here at the point 1 and 1, 2, 3, 4, 5, 6, 7, 8, 1, 8. So if my y value is time, it's going to take 8 seconds. Okay, now today's lesson, which is a quick one. You're going to need your book, but first you're going to just fill in the notes that you were given. Talking about systems of equations, as you may have guessed from the warm-up. System of equations is just a set of equations that have the same variables. There's 2 variables usually. If you have three equations, you might have 3 variables. We're just looking at 2. Solutions of a system of equations are the points where their graphs intersect. So in our warm-up, we had two intersections. At the points of intersection, the coordinates are equal. So that means the x and y coordinate are the same for both functions at that point. So at this point, I don't need that, I need this. At this point, the x and y value is the same for both functions. If I plug a 2 in, I would get 8, 2 in for x, I would get 8 for y. That's what that means. Okay, they may have infinite number of solutions if they basically overlap or they're the same function. You might have the same function written in 2 different ways. And we call that a dependent system. So they're dependent on each other. They're the same. The equations intersect. You have a finite number of solutions. This is infinite because the graphs go on forever in both directions. So they have an infinite number of points that they have in common. In this case, they don't. They have only a certain number of points in common, the points where they cross. We call that an independent system. So in this case, you've got an intersection right here, you've got a point of intersection here, and you've got a point of intersection here, and you can figure out those coordinates. We're going to learn how to do that using your graphing calculator. If they don't intersect, there are no solutions, and we call that the empty set. And then as we do these, we're going to look at the different types of functions we studied at the beginning of the class, such as the linear function, You might have to use the back of the page as we list these also. Flip over your paper if we run out of room here. And that looks like f of x equals x, and your graph is just a straight line. The parent function goes through the origin. And then you've also got your quadratic function, and that's f of x equals x squared. And that's a parabola. The parent function has the vertex at 0, 0, and it's facing upward. Next we had the absolute value. And I just want to remind you how to graph that in the calculator. Remember, it's math num number 1 to graph absolute value in the calculator, and that's f of x equals absolute value of x. And then that is a V shape. And then we have two more. So if you didn't flip over your paper, you're probably going to need to now. We've got the cubic, or any other polynomial. It's going to have a different curve shape, but we actually looked at cubic. So f of x equals x cubed. You might have a higher power that you get. You're just going to see more curves in it, as we learned when we talked about graphing polynomials a couple weeks ago. The cubic parent function looks like that. And the last one that we want to remind you of is the rational function. And that's f of x equals ab to the power of x. Not rational. I don't know why I called it rational. Exponential. Let's erase that. I have no idea why I said that. Exponential. Exponential because the power is a variable. And that looks like it has a y-intercept at 0, 1, and then it increases. It doesn't cross the x-axis, increases to infinity. Okay, those are the functions. Now let's go back to the book and do the examples. So if you go to page 172 in your book, you'll see this page, this graph. If you're given a graph and told to find the solutions, you're just going to go to the points where the two graphs intersect. Here, here, and here. And we can see this point and this point are going to be easy, but this one we're going to have to kind of estimate. That's why it says estimate the solutions. So I'm going to say this one, if I start at 0, 0 and go back, I go to -3, so my x value is -3, and then the y value is -70, so -70. So -3, -70 is that one. Let's skip this one and go to this one, because that one's easy too. So our x value here is +3, and the y value is 50. Now this one, let's think about it. I know it's between 0 and 1, and it looks like it's less than a half, because it looks like this is a half. So I'm going to say that's about 1/3, because it's not a fourth. And then I'm going to say this one is a fourth, because if I go down, that looks like it goes about a quarter of the way to -10, but it's a fourth of -10. If you look at your scale, well, a fourth of -10 is 2.5, or 5/2. You could put it in decimal, I don't care. So that's what you would put for your solution there. You have 3 points of intersection. This one, I want you to change it to, it says to use a graph, but this one you can get in the table. So I want to change this to the table. Use the table. Okay, so how would I do this? Well, what do we do for the warm-up? We put the two equations in the calculator and then looked at where they intersect. So that's all you're going to do. Clear out your two functions you had in there. Enter these, so 4x plus 1. And then this was absolute, or it's cubic, not absolute value. Okay, you've got your two functions. You just hit zoom 6 or just press graph, because you should already have it on the standard window. For all of these, you'll just hit zoom 6 or just press graph. Okay, so how many solutions do we have? 1, 2, 3. And this looks like it's around -2. The x value is around -2. This one looks like the x value is 0. And this one looks like 2. So if I look at the table, if I find -2, I notice there's the y values are the same. So that means on the first function I graphed, the point -2, 7 is part of that graph. And for the second function we graphed, the point -2, 7 is also on that graph. So one of the solutions is -2, 7 because they have the same, for the x value has the same y value. And we thought 0 might have been another one, so let's look at 0. And sure enough, our y's are the same. So 0, 1 is another one. And looked like we had one at 2, so let's check 2. At 2, yes, the y values are the same, so 2, 9 is the other solution. Okay, so if you can see the solutions in the table, you don't have to do anything else. If you can see there's 3 solutions and you can see what they are in the table, you don't have to do anything else. But if you can't, then there's a trick on the graphing calculator to do. So in this one, you're going to use the graph. So it's backwards from the way that they wrote it in the book. So again, you're going to put the functions in your y equals menu. And we've got absolute values, so math, arrow to the right to num, number 1, and put the x plus 4 inside, cursor to arrow out, and then plus 1, and then x to the 4th, plus 3, x cubed, plus 1. Okay, and then we're going to just press graph. Hopefully they'll cross where we can see them. Okay, I see 2 solutions. It looks like there's one around -3 and around 1. But the table doesn't exactly give me the solutions if you check the table. At -3, the y values are different, and at 1 they are too. So they're probably really close to each other. They're probably really close to 3 or 2, and for this one, 6 and 5, but we don't know what they are exactly. So we're going to use second trace number 5. We want the intersection, number 5. Okay, and then you're going to take your spider. It wants first curve. Well, I'm going to do that first point on the left first because I like to work from left to right. So you just put your spider somewhere near that first point and press enter twice. And then guess. That intersection is at -3. If we round it to the nearest tenth, it would be -3.0. And this one rounds to about 2. So the point is -3. The y value is 2. So -3, 2. And then if I do the same thing, second trace, number 5, and just move the spider up to the other point and hit 3 times. 1, 2, 3. The intersection there is at about 1.1, if I round that, and 6.1. So 1.1 and 6.1. Okay, and the last example, they give you the table. What conclusion can we draw? In other words, what are the solutions? Is there any, from this table, can we say that this system has a solution or more than one? All you do is look at the y values. Where the y values match, it's a solution. So it looks like this is the only solution. So the x value is 1, the y value is 5. Okay, so you're going to do the assignment starting on page 175. Page 175 through, and it goes all the way to 177. It's just because there's a lot of graphs, number 1 through 10. So refer to your examples to help you.